Hello folks, Professor Fiore here. We've got a nice video for all you folks that are just starting off on your journey in electrical engineering and technology. And that is a very important piece of lab equipment, which is an electronic protoboard, also known as a solderless breadboard. What's the deal with the protoboard? Essentially, this serves as a substrate so that you can construct your circuits. In other words, instead of trying to sort of wire components together directly or on a perf board, which you would have to solder, the solderless breadboard or protoboard allows a very convenient way of creating the circuit, putting components in, pulling them back out. You don't have to pick up a soldering iron. It's very convenient. All right? They come in various sizes. I'm going to look at a typical size here. The holes that are on here, and you'll find them that have 96 holes, 144 holes, 200 and however many holes. The holes are sized so that you have 1/10 inch spacing. And the reason for this is because that is the spacing for common through-hole integrated circuits. Right? So something like an operational amplifier, for example, or a digital logic, a small-scale integration digital logic circuit like a gate. That would be the standard sizing. So these protoboards are designed with that in mind. Now you might say, hey, wait a minute. What are you talking about? Through-hole integrated circuits. Isn't everything surface mount nowadays? Well, yes, it is. If you're doing commercial, large volume sorts of consumer products, yeah, everything certainly is surface mount. Not practical, though, when you're in the lab just learning about electricity and electronics. You'd have to go in there with tweezers and a magnifying glass in order to build circuits and test them. So we still use standard through-hole components, right? So things like low-power resistors, inductors, capacitors, diodes, transistors of various kinds, bipolar, field effect, whatever. Those transistor leads and component leads will fit fine into these little holes, right? They're also designed optimally to work with 22 gauge solid hookup wire so that you can jump points to points to points to points. And there are also, as you'll see, long strips or buses that you can use for tie points that have many connections. For example, a ground bus or a power bus, right? And typically you'll see at least 2 of these, very often 4, sometimes more. It all depends on how it's hooked up. Sometimes you can go out and buy these things where there's 2 or 3 of them together on a plastic or a steel sort of backing, a frame. I kind of like the very simple little ones that are all by themselves. They're not mounted. They're relatively inexpensive. You can throw them in a backpack. They don't take up much space. A couple of caveats here. First of all, these things are not designed for very high power applications, and they're not designed for very high frequency circuits. Those things, you'd be better off going a different route, but we don't have to worry about that here at the front end of the journey when we're just trying to figure out basic series circuits, parallel circuits, things like that, how to connect these things together, how to do current measurements, voltage measurements, and so forth. Okay. Now, the one thing I do want to point out is there's a million ways for any individual to create a workable, in other words, legal, electrically speaking, layout on a protoboard given a certain schematic. Right? I could give a schematic to 5 different people and get 5 different things as far as the protoboard, and they're all properly connected. But some of them are better than others. Some of them are more practical than others. Some of them will be more prone to errors on the part of the experimenter. All right. So my pro tip here is create a protoboard layout that is similar in appearance to your schematic. Right? Bear that in mind. Okay, so what is this thing? Well, here's your basic protoboard right here. All right, so I've got a little integrated circuit right here in the center. And what you see is just, holes, 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 holes. Okay, so the holes here are 1/10 inch spacing. And basically the way it works is that there are rows of 5 pins that are common, right? Each row is common. So now I've highlighted a row here in green. All of these points are a common point. This row over here in yellow, all common, all right? So when you throw an integrated circuit in here, right, a lead comes in and you've got all of these remaining, in this case, 4 tie points for other components to connect up to. Then along the sides, we have the buses. So this is in sort of a lavender purplish kind of thing. That whole thing is one bus. So there's 2 on this side and there's 2 on this side, right? So there's 4 buses total. Now, something to be aware of. Very often you will find these boards this size. This is a very common size. It's a good size. You will very often find these with holes at the corners and halfway down so that you can mount these on some kind of carrier, right? You know, a backing of some sort. If your Protoboard has a hole here and here, right, for that mounting, then these buses will most likely be discontinuous all the way down. In other words, you'll actually, on this side, instead of having 2 buses, you'll have 4. So there'll be a pair of buses coming up to that hole. That hole breaks the connection, and then there'll be 2 more buses coming up here. So what a lot of students will do if they don't mount it on something, and like I said, there's really no reason to, they'll just get some small jumper wires and jump over where the hole is so that they have 2 long buses on this side, 2 long buses on that side. I find that to be pretty useful. It's very rare that you would have to have, at least with the kind of circuits we're going to start off with, that you would need to have 4 buses, more than 4 buses. So, you know, 2 long on this side and 2 long ones on that side, that's sufficient. All right. Okay, over on the side here, I've got a close-up. This is what's inside, right? So I said there's a row of 5 pins. This is what's inside. So we've got this little spring clip, this little metal spring clip. You can see it's sort of a U-shaped thing. The top of it clips together, right, touches. So you insert a wire down in here, and it basically separates these little fingers, right, and makes a connection, right, because this is one solid piece of metal. So you put in different pieces of wire or different different components and so forth, and they're all at a common point. It's all a node in electrical terms, all right? You do not want to put more than 1 wire in a hole. Okay, these things are, like I said, sized for 22 gauge solid wire. You don't want to use stranded wire. You don't want to use a wire that's much larger than that. You know, you could try to jam something in here, but that's potentially a problem. Okay, you could break these springs, have poor contact. Same thing if the wire's too small. If it's too fine, you try to put in like maybe a 28 gauge wire. You know, you're not necessarily going to have good contact. So stick with the 22 gauge solid hookup wire, 1 connection per hole. Okay, if you need more than that, you can always jump one of these to an adjacent row, a row somewhere else, and pick up more connections. So here's a little thing just to remember how this works. What I've done is I've taken this board, flipped it over, and usually there's just a big piece of like sticky plastic on the back. Okay. And I've peeled that back, and this is what you'll see, right? So that backing is gone, and each one of these little things is the spring clip. There's a spring clip. So a whole bunch of these are missing so that you can see, right, that, you know, the other end, here's the holes, right, that you saw a moment ago. And now that you look at it, you can see just how this thing is connected up. Okay, here's the long strips, the buses on the side. All right, here's the individual ones for the 5. And of course, here's the trough down the center. Remember, your integrated circuit is going to be sitting on here, so you don't want that to go all the way through, right? Right? Here's that trough. You don't want this section to connect to this section, right? You don't want the yellow to connect to the green. Then you'd short out the pins on the integrated circuit. So just remember that trough says, hey, there is no connection. It's broken here, okay? If you just remember this picture, it'll hopefully stick. You'll understand how it works. Okay, so like I said, you know, if you have the holes and you did this, and by the way, don't do this, don't peel this off because it'll probably not stick when you try to put it back on. Just trust me on this. Essentially what happens is this silver bus ends here and another one picks up on the other side of the hole. Right? That's why I said you would have 4 buses on this side rather than just 2. All right, great. So now, we understand how this thing works, right? It's just a bunch of these spring clips, you know, a huge bunch of these spring clips. so that you can connect wires together. All right, so you take your resistor, capacitor, transistor, whatever it is, you stick a lead in here and off you go. Now a common error that people do is they put both ends of, let's say, a resistor in the same row. And what you will have done is you shorted out the component, right? Because this is just a wire, basically. That's the way you got to think of it. Every one of these rows is a wire. So if you put a component like a resistor, one lead in here like A, and the other lead over here in D, you've basically shorted out that component, because the current will always take the path of least resistance, meaning it will go through this little metal spring clip rather than going through the resistor. All right, that's a very common error. Another common error is you miss a row by maybe one position. In other words, I want to put a resistor in and I put it in this row labeled 55 right here. Okay. Now I want to jump that to another component. And I accidentally, put the wire in this hole, right, which would be like row 56, or back here, row 54. That's a pretty common kind of thing, right? And you can stare at a Protoboard all day, if it's your own work, right? It's like trying to proofread your own writing, your own lab reports. You can stare at it all day and not see the error, and then somebody else will walk by and go, "Oh yeah, it's right there. You missed a hole." Okay. All right. So now let's go and turn our attention towards making a circuit, right? So you have a schematic. You open your textbook, and there's a schematic, and you want to be able to build this thing to test it, right? You got a lab manual, let's say, and there's a schematic, and you have to do some measurements, right? Verify some laws and so forth. So I'm going to start with a little basic series circuit. So I've got a 10-volt power supply, and I've got 3 resistors, a 1K, a 2.2K, and a 4.7K. So here's a recommended way of creating this, right? So I go over to the bin, I grab my 3 resistors. I don't have brand new spanking resistors here, right? You can reuse these things. Off on the side, these 2 leads represent the positive and negative power supply connections. And we usually, in electronic work, black would be ground and red, or white sometimes, but typically red, would be the hot lead, right? The plus lead. So if you've ever done house wiring in the US, this is a little weird. In house wiring, black is the hot lead, right? But in the electronics industry, no. Black is a common or a ground, all right? And red over here would be the hot lead, all right? That's the standard that we use. So when you look on the power supply, there's probably a couple of banana jacks there, coated red and black, so continue that color coding. So what I've done is, since these are just alligator clips, I've taken some little lengths of wire, 22 gauge wire, right, stripped the ends. And by the way, you can buy little kits where they've got chunks of wire that are already stripped. I think it's a lot cheaper just to buy a spool of wire and start chopping off chunks and get used to learning how to use a wire stripper. Get some different colors. Don't always get the same color, but in any case, so I've grabbed a little piece of red wire here, connected my positive terminal of the power supply to it, and then the other end goes into one of the buses, right? So this whole thing over here, this red strip, right, which is actually labeled B. I don't know if you can see that in the video, but this whole thing is common. This is all the same, right? The one toward the red strip. So then what I do is I take my R1, the 1K, put one end into that bus. So here's that wire going in. And then the other end gets connected to a 2.2K ohm. So I'm going to pick that up and put it pretty much wherever it's convenient on this Protoboard. But again, I want to make this look something like my original schematic. It's going to be easy for me to go back and forth between this thing and this thing, right? So make it look the same. So I just bring this out here to somewhere convenient, and then the 2.2 will go into that same row, right? So here's a row of 5 connectors. So I take one end of the 2.2K, right, red, 2.2K, and I put it in that same row. Doesn't matter which hole, because I got 4 left. That spring clip is going to connect this point to this point, this lead to this lead, all right? Then I take the other end of that resistor, put it on the other side of the trough, okay? And then, because now it's going down, right, kind of vertically oriented in my picture. And then I do the same thing on the other side. I connect that to the 4.7K, right? Again, so here's a strip of 5. So there's one end of the other end of the 2.2K, and then here's one end of the 4.7K, right? So there's our yellow, violet, red. And put that in there, and then the other end of that goes back to the negative power supply, which is ground. So put that down here on this lower bus. The black lead came in. I've got a little brown jumper wire coming down here into this A bus, the blue bus. So that's my ground. And there you go. There's my connection. So I can go back and forth between this, and it's really obvious what corresponds to what. And now I can consider, making voltage measurements, current measurements, whatever the heck it is. But as I said at the outset, there's a gazillion ways to build this. Some are better than others. This is not a good way to build it. All right, so I'm not using the buses. I just have this first resistor, that's the 1K. Notice it comes into this thing over here. Then here's the 2.2, which picks up, goes out further. I'm doing this all on one side now. And then, this other lead kind of comes down in and goes into that same thing, comes back to another random spot, and I pick up another jumper and go back to the negative side of the power supply. So, I mean, this is correct technically. The current goes in first through the 1K, then the 2.2K, then the 4.7, and then back to ground. There are no breaks in the circuit. There's no components shorted out. But it's really not the best way to do it. When you have bigger and bigger circuits, doing it like this, it gets confusing very quickly. You can accidentally have components shorting out each other, like leads touching other leads that they shouldn't be. Another shortcut that some people will do is they won't even use these jumpers. They'll just take the power supply and connect it right to the component. I don't recommend that you do that. It's too easy to move the board and have this thing, pull off. Now I've got a component dangling in midair, right? You don't want to do that. Okay, so again, we look at this. It's obvious what's happening. It echoes our diagram. Okay, this, not so much. Now, I want to do a volt measurement. So here's my schematic. Here's my voltmeter. I want to measure, in this case, the voltage across R2, the 2.2K. So the plus lead has to go in between the 1K and the 2.2K, and then the minus lead has to go between the 2.2K and the 4.7K. So here's my diagram, right? The lead over here is going off to the plus. That got cut off in the picture. But there's my three components. So all I have to do is take my voltmeter, and I've got my two leads over here, right, for my multimeter, set that to volts, DC volts. And red lead, again, the plus. I just connect that here, one end of the 2.2K, and then the black lead, the other end of the 2.2K, and off we go. Now, I'm doing this with alligator clips, right? Just so that it was easy to do the photograph. But of course, with a DMM, you would probably have probes, right? Little sort of needle nose kind of probes. And you would just have to touch the red end here and the black lead there. You wouldn't actually have to get clips, okay? If you have to do multiple connections and you're going to change stuff, okay, clips are good. But if you're just going to go around here and say, hey, I want to measure this voltage and this voltage and this voltage, you just get those two leads, touch the ends together, touch them on the ends of the component of interest, and off you go. All right? Beautiful. So voltage is always measured across a component. Remember that. What about current? Well, suppose I want to measure the current that's circulating here that I find flowing from the 1K through the 2.2K. Well, currents are always measured in line, right? The current has to flow through the resistors of interest through the ammeter. So you have to break open the circuit. And this is where things get a little interesting. If you were kind of sloppy and just sort of throwing stuff down here, this is where inadvertent errors pop in. So what I'm going to do, because I know I have to break the circuit, I'm just going to grab my 2.2K and just move it. Or you could also, move the 1K. It doesn't really matter. But these two things originally were in the same row. Okay, if we go back here, you can see it there, or maybe a little better. Oops, one more. Right there, right? They're in the same row. So I pick one of these up and move it over, right? So I can take the 2.2, I can move it over to here, or take the 1K and move it over to here. I just have to break them. Okay, so I break them, and then I insert in that break, because that's an open circuit now, I insert in that break the ammeter, right? So here's the red lead going off to the ammeter, and then the black lead coming back from the ammeter, all right? If you get these backwards, you're going to get a negative current. Just like if you flip the leads on a voltmeter, if you get them backwards, you're going to get a negative voltage. Okay? All right. So current goes from the power supply into the 1K, then it has to go through the ammeter, back, go through the 2.2K, down through the 4.7, back to ground, in other words, back to the power supply. So there's your complete loop. All right? Beautiful. Common error. Common error is people will wire the ammeter as if it is a voltmeter. All right? So what do I mean? Like you wire it like this, but you have the multimeter set as an ammeter. What does this do? Well, the internal resistance of an ammeter ideally is 0. And what you'll have done is you'll be measuring a current all right, but the ammeter will have essentially shorted out the 2.2K, and you've got a different circuit now. Right? You only have a 1K and a 4.7K, so you're going to get a much higher current than you would have you done it the right way. Okay, so that's basically what we're looking at for a series circuit. Right, now let's move along to a parallel circuit. So a parallel, this is where the buses come in very handy. So you notice that all the resistors are connected to the positive power supply, and on the other end, they're all connected to the negative end of the power supply. So again, here's my 2 leads. Right, the red alligator clip is off screen here, but this red lead's coming down. And again, this red strip, right next to the red strip, that's my positive. And then this blue strip down here, that's my negative. So I take my 3 resistors, 1K, 2.2, 4.7, bing, 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 and I just jump them right across. Right? Piece of cake. That works out really good. I mean, look at the correspondence between this visually and this. Right? It's great. Everything is very easy to see. Now, if you want to do a voltage measurement, well, you pick up your voltmeter. You want to measure the voltage across the 4.7K. Same thing we saw before, right? Red lead here, black lead there. Same thing with the 2.2, the 1K. You get your voltages, right? It should be the case in a parallel circuit that all the voltages are the same, right? That's the thing about a parallel circuit. What if you want to measure current? Well, again, you have to break open the circuit. So if I want to get a branch current, like let's say the current through the 4.7K or the current through the 2.2K, I'm going to have to pull the resistor out of the bus, put it off to the side. I have to break it open and then connect the ammeter between where the resistor is now and where it was. Okay. So here I am measuring the current in the 4.7. So I lifted the 4.7 off of the bus, and I just happened to put a pigtail lead where it was. And now I connect my ammeter between where it was and where it is now, right? Just lift it up so there's that break, okay? So now the current comes in here. Some of it comes down through the 1K, some of it goes through the 2.2, and then the rest of it comes out here, goes through the ammeter, and then down through the 4.7, and then back, right? Exactly as shown in my little schematic. All right, so far so good. You want to do it for the 2.2K, same deal. Return the 4.7 back to where it was. Lift this end of the 2.2K, put it out here somewhere, right? Put your pigtail over here for your ammeter. Same thing, black lead over here on where the 2.2 is now. Repeat the process. What if you want to measure the total current? In other words, what if you want to measure the current back here? All right, current coming down through here. Well, we'll pick that up in just a sec. Hang on. All right, last one, series parallel circuit. So we got some series, some parallel. Right? These 2 resistors are in series, and that combination is in parallel with this first resistor. Right? So now we're actually a few chapters into the book, but I just want to show you the same technique of building. Right? Make it look like the schematic. Again, positive power bus, ground bus. Here's a 1K going from positive to ground, so just run from bus to bus. Here's a resistor coming off of the plus, right? The 2.2K is coming off the plus, so here it is, coming out. Bring it somewhere, doesn't really matter. I just happen to bring it on the lower half, pop it in, and then pick up the other resistor, the 4.7, from that point, bring it back to ground, right? So there we go. These 2 are in the same hole, bring it back to ground. Common error. One of these leads is like 1 hole over, right? Like the 2.2's over here, or the 4.7's over there. Now you got an open circuit. All right, that's a very common kind of error. All right, got to watch that. Got to keep your eyes open. So there's my circuit. Now let's do some measurements. So I'm going to do a voltmeter. So I want to measure the voltage across 4.7K. Nothing new here, nothing different. I take my voltmeter, red lead on the top end of the 4.7 where it connects with the 2.2, right? There's the connection. So there's my red lead, and then my black lead goes on the other end, which is ground, right? The bottom bus. Beautiful. Again, I'm using alligator clips here, but in a case like this, you're just going to pop around and measure various voltages. You're just going to get your DMM probes, right? Just touch the ends on the components, and off you go. All right, what about current? So if I want to get the current between, right, R2 and R3, again, you're going to have to break these two resistors apart. So what I did is I lifted this end of the 2.2. Remember, it was down here. All right, let's go back. All right, so these two things were together. Okay, so I lift the 2.2 off that, put it on the upper end, so that creates a gap. That's now an open circuit, and that's where I insert the ammeter. Right, red on the 2.2K side, black on the 4.7K side. So now the current has to go down through the 2.2, through the ammeter, and then finally through the 4.7, which is exactly what's happening here, right? Again, make it look like the schematic, okay? So much easier. Now, what if you wanted to measure the total current back here, right? This is what I was sort of sneaking in just a moment ago. Here's your original circuit again. Well, if you want to measure the current back here, that's the current coming out of the power supply. So here's my power supply lead. And what I do is I just unhook that from the lead that I had that was going in. In other words, this thing, right? The red clip is out here. You can't see it. All right, so I unclip that. There's this other red alligator clip is the ammeter, comes out through the ammeter, black lead of the ammeter, put it back on where the power supply was, and now that connects up to the bus, and everything's hunky-dory. All right, so key takeaway. You've got all these connectors, 1/10" centers. Make sure you make the circuit at least echo what the schematic looks like. You know, I mean, the circuit itself doesn't matter, right? I mean, gravity doesn't affect these things. This could be upside down, you know. There's a zillion ways of making it, but why make it more difficult on yourself, right? Make your life easy. Make it look like this, and then off you go, okay? All right, I hope that covers the basic idea, right? You understand how this Protoboard works, solderless breadboard. Extremely useful little device. You know, pick up 1 or 2 or 5, you know, whatever. They're relatively inexpensive, and they are indispensable. Okay, take care, and we'll see you next time.